Okie doke. So the third case, which is the oil, at least the oil, the way that Golosov et al. Modeled it, right? If you remember, they modeled it as free to extract, just like in DHSS. So this is basically the DHSS case, but instead of zero technological progress, zero depreciation of capital, we're assuming depreciation of capital and positive technological progress. And we're endogenizing the saving rate S to make things easier. And for now, we're just going to assume that the flow R declines at a rate theta, which, if you remember from the DHSS analysis, this makes an awful lot of sense, okay, at least on a balanced growth path. So then we're told to solve for what happens on the BGP. What can we say about the initial rate of resource consumption? So let's have a look at that. I've got a new plan here. I'm going to show this in the corner, and let me see. I'm confused now. Yeah, there we are. Okay, so we can still see that picture there. Okay, so this stuff is all going to look the same. Of course, this X disappears, but we're going to end up with this again and this. But now R dot over R is minus theta. So Y dot over Y is, so this again is Y dot over Y. So that's 1 minus alpha Y dot over Y, divide through. So it's 1 minus beta over 1 minus alpha. G again, but now this is minus theta, minus beta times theta, divided by 1 minus alpha. Oh, minus beta over 1 minus alpha times theta. Okay. So now we've got two factors breaking the growth rate, G. Instead of Y dot over Y is G, we've got this factor that is that, if you like, the resource flow can't grow, but then actually it's shrinking. So that reduces the growth rate even further. Okay, so solve for the growth rates on the BGP. What can we say about the initial rate of resource consumption? So again, we looked at this briefly before, but if this is time and this is R, we know it's on an exponentially declining path. We've been told that by assumption. This area has to be equal to the initial stock, right? So what's this area? It's the integral between 0 and infinity of, that's R0 e to the minus theta t dt. I think that makes sense, right? I don't have any notes for this. So that integral has to be equal to like S0, the initial stock. So what is this integral? Well, if we differentiate an exponential, remember it's integral with respect to time, we get minus theta times this. So when we integrate, we need to divide by minus theta. R0 over theta minus e to the minus theta t. So we can check this, differentiate it back, we get that, yeah. So that's the integral. We don't need to worry about the constant because we're doing it between limits. Put in infinity here, this is just 0. Put in 0, and it's e to the minus, sorry, it's e to the 0, which is 1. This is a plus sign, this is a minus sign, so the minus signs go out, and it's R0 over theta, which must be equal to S0, the initial stock. So R naught, which is what we wanted to find out, is theta S naught. So the bigger the rate of decline, the steeper this goes, the bigger the initial consumption. If we're super impatient, theta will be big. We'll have a lot of consumption early and then a steep decline. Okay, and that will give us a lower growth rate. And of course, if we make theta too big, we'll have a negative growth rate, which Solow wouldn't like. If you remember, Solow was interested in how you get a constant consumption. Okie doke. Let's look at the next slide. Assume perfect markets and symmetric equilibrium. What can we say about the resource price? I don't know if you can read this, but actually I need to just take a little break. So I'll just pause the video here. Okie doke. So, second part, we're going to look at what happens in the market with this limited resource costless to extract. Assume perfect markets and symmetric equilibrium. What can we say about the resource price? And this is basically hoteling. I'm not going to take you through it again. I know I maybe should have done it better, but I think you can study this on your own. There's a lot of resources out there on the internet. Basically, if we call the resource price WR, then hoteling tells us that WR dot over WR, the growth rate of the resource price, must be equal to rho, which is going to be the market interest rate, which is the pure rate of time preference. Simplest way to think of it is the resource stock is an asset. The price of that asset, if you want to hold that resource stock, the price of that asset must grow at this, or the value of the asset must grow at the same rate as the value of other assets. The value of the resource stock grows through the price growing. So if it's not growing at rho, then it can't be an equilibrium. Okay. Right, so we know that the resource price is growing at a certain rate. How do we use that information? We need to set up a profit maximization problem for the users of the resource, right? So this result is coming from the supply side, right? From the mine, so to speak, or from the oil well. But now we want to look at the demand side, right? So what's the profit of someone demanding the resource? It's PYY, but PY is normalized to 1. So it's Y. I should really write out the expression for Y, but I'm not going to. Minus the input costs, which is WLL minus WKK. WK is the price of hiring capital, minus WR. So if we take the first order condition with respect to R and put a colon here, we get, this will be WR, and we shift sides so the minus sign disappears. We'll get WR equals dy dr, which is beta times Y over R. Okay, so far so good, but the expression we had was for the growth rate of WR. Well, then we need to differentiate this with respect to time, don't we? WR dot over WR is Y dot over Y minus R dot over R, because these exponents are both 1. But minus R dot over R, well, we know that it's theta, right? And actually the whole point is we want to find what theta is going to be. Well, actually, yeah, so in a way we don't know it. It's called theta, but we don't know what level it has. So yeah, we want to find this out, don't we? But on the other hand, what we do know is y dot over y, at least in terms of theta. So basically, we've got a lot of things that we know plus theta, because wr dot over wr is rho, y dot over y is 1 minus beta over 1 minus alpha. Well, no. Actually, I think I'm going to leave it in terms of y dot over y. Rho is y dot over y plus theta, right? Because r dot over r is minus theta. So theta is rho minus y dot over y. So I'm just going to pause for a second, which is, so I do need to substitute in for y dot over y from up here. It's rho minus let's do it this way, minus g minus beta over 1 minus alpha g plus theta. I think that's right. Yeah. So if we take this over, take this bit over, we get theta, oops, I'm going off the page. Theta times 1 plus beta over 1 minus alpha is equal to rho minus g. I feel like I've done something wrong here. 1 plus beta over 1 minus alpha. So minus g times that. So that's minus g blah blah blah. So theta, according to this, is rho over that term in brackets minus g. But I'm not totally sure that's correct. I just got to pause and check through this. I think I made a mistake somewhere. Okie doke, sorry, I did make a small mistake. It just didn't feel quite right. Minus y dot over y is minus g plus minus y dot over y is plus beta over 1 minus alpha g plus theta. Okay. So then we end up with minus here. Okay. But really the most interesting result is really here. Okay. That if we observe the growth rate of GDP, y dot over y, and the interest rate, rho, then the growth rate of, or the decline in resource use will be equal to rho minus y dot over y. So we're back with the result that we said doesn't fit. Sorry, we're off the page here. We're back with the result that we said doesn't really fit the data, that if we plot on a log, this is time, this is GDP, these results say that the price of the resource should be growing more steeply. That should be WR, the growth rate, whereas the resource use should be declining. Okay, but that's what would happen in this model if we ended up in this situation, right? That we're totally dependent on something like oil that is very cheap to extract and running out. Okay, I'm gonna stop there. I think, let me just check. Yeah.